Someone else speculate, something other than the middle.
The point at which the meter stick, doesn't like move to either side.
You mean the center of mass,
Yeah.
which should in theory be the middle. But this thing's not gonna be rotating anyway, in theory. So we're gonna have a different guess besides the middle. Someone pick another spot. Oh, I just said something. Somebody name a location in the room. I'll wait this one out again. Pick some point on the meter stick.
Could be one of the points that it hangs from.
Okay? How about someone who hasn't spoken today? Is silence that, is there a fear of being wrong, or is it just that you don't know what the question is, or you are just really shy right now? I guess you're really shy, I won't get an answer back. Well, you don't need to fear about being wrong, so if that's the holdup. You know, it's such a small point, I'm gonna move on, but wow. It's okay to speak. Because there is no natural rotation point, I mean, you could sort of make an argument that perhaps the center of mass, but because of the way it's suspended like this, not necessarily. If we suspended it from the center of mass, you know, like when you put the meter stick on the fulcrum holder and to see where it would balance, in that case, yes, I think there was a natural spot. But in this case, I think you could easily make an argument that there's not a natural spot. You can pick any place you want. So let's calculate the torque about this point right here, and then we'll calculate it about this point right here. So I'm gonna call this point A, call this point B. So from point A's point of view, 0.2 meters, 0.7 meters. And then the next one was 0.5 meters, 1.5 newtons. Oh, that should have been 0.7 newtons. And then the third force was 0.9 meters and 0.8 newtons. What is the torque created by this force right here about that point right there?
The force at that point?
What is the torque created by that force about this point? And the language is, since torque depends upon where the axis of rotation is, that's why I'm specifying about this point. .14. So 0.14. Give me the whole thing.
Newton meters, Newton meters.
In which direction?
North.
Let's assume that this,
Okay.
that holds true.
Positive direction?
Which positive direction?
To the back of the building?
Yeah, okay.
Okay.
So, give myself a little bit more room there. Positive 0.14 Newton meters K, just because I said K was coming out. What is the torque created by this one? The torque created by this force about the left end.
Negative 0.75, right? Newton meters.
Yep. They're perpendicular to each other, just multiply 0.5 times 1.5, 0.75. Or half of 1.5 is 0.75. Or half of a $1.50 is 75 cents. And it's negative because it's trying to rotate it the other way. And the torque here. The torque of the 0.8 Newton force about the left end.
Newton meters. Okay, positive.
Yep, it is positive. All right. So we have the torque from each of those. If we add them up, what do we get? So even though this is in linear equilibrium, because the force is up equal to force is down, this is not in rotational equilibrium. Or if it's lab data and it's a meter stick sitting there, so you know it's in rotational equilibrium, the results are not telling us that it is what we know it to be. Because it's a physics lab, and physics labs are rarely that good. So now let's take the exact same thing and let's find the torque about the center. So we've got the center here with this force acting down of 1.5 newtons. And then, since this is now our reference here, this will be 0.4 meters to my 0.8 Newton force. And then over here, this is 0.3 meters to my 0.7 Newton force. Again, I have three forces, so potentially three torques here. So the torque from the 0.7 Newton force is what?
Are you saying that for the 0.3 meter segment?
Right, since we're finding the torque about the center now, so what is the torque of the 0.7 newtons about the center? I heard 0.21 newton meters?
Yes.
What about the direction?
Positive.
You said positive and then you hedged.
Cause is it, are we doing positive as like up and down or left and right? Or is that
in and
like
out.
up to us?
There are two ways of doing it, but right now we're just doing it by which way, if this is my axis of rotation, that 0.7 Newton force is gonna try to cause it to spin which way?
Upwards, right?
Or clockwise?
Yes,
Okay, so it's gonna try to spin it around like that,
yeah. So, negative.
so it's negative K. The torque of the 1.5 Newton force. Actually, let's do the 0.8 Newton force first, and then we'll come back to the 1.5 because it's a little bit trickier. So the torque of the 0.8 Newton force. The torque of the 0.8 Newton force about the center.
Minus 0.45.
Not 4.5. Did you get 4.5?
Okay.
So are you doing the middle one?
Yeah, 1.5 with 0.3.
Nope. That it's a little bit simpler than that. So this one right here,
0.32?
since we're doing it about the center here, it's 0.8 newtons times 0.4 meters. So 0.32,
Newton meters.
and then direction.
Positive.
And now we have this middle one, which is not 0.45 or 4.5. I guess 0.45 if you multiply those two.
Would it be 1.5 newtons times 0.1?
You- We can point the
It's
difference
in
between the two.
middle, yeah. So,
Because remember, torque is trying to cause angular acceleration, trying to get something to rotate. The 0.7 Newton force is trying to rotate it clockwise. The 0.8 Newton force is trying to rotate it counterclockwise. But if we're pushing right there in the middle, and that's our reference point, which way will a force pushing right there try to cause it to rotate?
0.9.
nowhere still.
So the torque is 0. Whatever direction you feel like. There's no torque.
The distance is different. How will be 0?
Because if we go back to that torque is R across F, R is the vector from the axis of rotation to where the force is applied. So in this case right here, it's 0. R is 0. The equivalent to a door would be to try to open or close a door by pushing on the hinge. So the total torque now, 0.11 Newton meters K. It is just coincidence that we got the exact same number. Ordinarily, that does not happen. Now, another way of doing this to try to figure out the direction, if you were going with this, so to the right and up are positive, let's go over here. This 0.2 meters. It's going to the right, so that's positive 0.2. The 0.7 newtons is up. That's positive 0.7. And so we end up with positive 0.14. Here, this vector here is going to the right. So that's a positive 0.5. The force is down, negative 1.5. So we get negative 0.75. So you can, if you stick with a convention like this, you can also just figure out what you're multiplying with in terms of positive and negatives, and it'll tell you. Over here, this point, the 0.7, that 0.3 is to the left, that's negative, so it's negative 0.3 times positive 0.7, and you get negative 0.21. So in the lab, I try to take you through that route where stick to the right is positive and up is positive, so your R value will either be positive or negative depending upon which way that arrow is pointing, and force is positive or negative depending upon which way that arrow is pointing.
Can you explain why that middle one is 0 again?
All right, so torque is, you find torque about some point, where that point is your axis. So for a door, generally you're finding the torque about the hinge. So imagine that there's this line running along the hinge. So torque is something that is trying to cause acceleration. Well, if I'm pushing on the hinge itself, how easily am I going to open or close the door?
You're not.
That's because there's no torque being applied. Torque has, if you push on the axis, it's not going to rotate. That's why it's 0 conceptually. Is that sufficient?
Yeah, so we're just saying that middle point is the axis.
Right.
So R sits on where the force of 1.5 Newton is applied.
Yes.
So it's, okay, that's 0 times, okay.
Yes. And one of the reasons when you actually do this, if this were physics 151 or 251, where we get more into the hardcore math, you usually pick some point which is going to eliminate one of your torques. So if you have something like this where you don't have some natural rotation point, you would either pick this, or this as your axis, just so that one of the torques is 0. So a 151, 251 problem on something like this would be, we'd get rid of that and just say, where is this force located so that it's in rotational equilibrium? And so you introduce a variable x, and then pick some point that will reduce the amount of math you have to do. A great deal of time spent in more advanced physics of trying to find the coordinate system and an origin that will minimize the amount of math you have to do. And I guess that might change once they have a truly working quantum computer. Then it'll be so fast that you don't have to consider things to reduce the amount of math you have to do. Right. Questions at the moment? Because we're about to go to the races. All right. Let me grab your board. See here. So, clear some of the view. Yeah, I want something wider than that. Now, when doing this, well, hopefully you can see well enough. I don't want the board to be so steep because I'm going to roll stuff down it, and if it's too steep, then things are more apt to slide, and I don't want sliding going on. If it's too shallow, so that they're not going particularly fast, then all the bumps and eccentricities in the board start to have a more dominant effect. So there's some sweet spot to minimize the amount of slipping and to minimize the effect of the bumps. All right. So the question is, I have two round things right here. I'm going to roll them down the board, and the question is, which one will get down first, get to the bottom first? And I'm going to replace that with this one. That one's looking a little warped there. All right, so I have these two round things here. Which will get to the bottom of the board first? And let's reorient this.